Welcome to day 9. You got page 62 and 63 for your homework. Tonight we're going to work with the idea of independence when it comes to probability today. And there's no warm up, we're just going to go through the homework answers. So we had this diagram, this Venn diagram, and then we had to fill out the chart below. So 16 was instrument and foreign language, 30 was in the section for foreign language but no instrument, so then together that's 46 if you were to look at the whole circle. And likewise, you get each of the other values in the chart. So in part B, if the person selected does not speak a foreign language, so that tells you we are only focusing on this row. So only looking at that row, then what is the probability of playing an instrument? Well, it's 25 out of 34. The notation for that would be a conditional probability. You'd have P, I just used I for instrument, and then the vertical line means given the fact that they did not take a foreign language. If the person selected does not play an instrument, so this is telling us we should focus on the not instrument column. What is the probability the person does not speak a foreign language? Well, that's 9 out of 39. Again, the notation would be not a foreign language given not an instrument. That vertical line means given. So the bold one would be a statistic in 7A because it's just out of those people that are interviewed. In B, because it's based out of all people in Ohio, that number that voted, it is a parameter. In 8A, it's an experiment because they split them to random groups and they told the people to exercise 3 hours a week and then the other 50 to do something else. So they imposed the treatment on them. In B, they were asking questions. That's a survey. And in C, the reason it's an observational study is they just took people that were already doing that on their own. The researchers did not impose that treatment on them. So this is the intersection. We want to find the ones that are in both of those. So your factors of 12, 1 and 12, 2 and 6, 3 and 4. Factors of 16, 1 and 16, 2 and 8 and 4. So the ones that are in the intersection, so in both those, are 1, 2, and 4. Your complement of D, so D with the complement, two ways you can write it. You can do interval notation with a square bracket on 5 going to infinity, or saying x is greater than or equal to 5. Those mean the same thing. And in 11, if you're dividing them into groups first and then randomly selecting, that's a stratified random sample. So if you split them into groups and then do the random selection, stratified random sample. Number 12A, researchers doing what's easiest for them, so that's a convenience sample. In B, it's some pattern every 50th iPhone, so that's systematic sample. And because in C, all of them have a chance of being selected, that's a simple random sample. All right, so we are going to be starting on page 58 in the packet today. So we'll give you a moment to flip to that. And we are going to look at independent events. So two events are independent. If knowing that one of them occurs, it does not change the probability of the other outcome. So two independent events. Say rolling a die and getting a 5 is one thing we want to happen, and flipping a coin and getting a head. Knowing whether or not we got the 5 on a die does not change the probability of whether we got a head on the coin. So those two events would be considered independent. A dependent event is one where if we know the outcome of the first one, it changes our outcome of the second one. So say we want to pick two cards, one right after the other, and we're not going to replace them. The first thing we want is for the first card to be a 4. And then the second pick, we want the card to also be a 4. Knowing whether or not we got a 4 on the first draw will change the probability of whether we'll get a 4 on the second draw. So those would be considered dependent events. Now, those are two examples where hopefully it's kind of clear that it either doesn't change or does change. A lot of times, just from the events themselves, we might not know, so we'll learn a test of how we can determine whether they're independent or not. And there's two ways to do that. The bottom one is the one that we will work with more. So you can take your intersection, the probability of A and B, and you can see if that is the same as your individual probability of A times your individual probability of B. If those are equal, then they are independent. So that's key. This is the test for independence. So when it works out, that means independent. If it doesn't work out, then that is dependent. Now, the other way to do that is with a conditional probability. So this is read as the probability of B given that A happens. And it must be the same as probability of B. Well, given that A happens, that basically means if you know the first event happened, the probability then of the second event is the same as just the probability of that second event overall. So that additional information of knowing that A happened did not affect the probability at all. We're going to look at that once or twice today, just so you can see an example of it. But the intersection one, the one with the and, is the one that we'll use more frequently. All right, so going on to page 59. So we have a single die is rolled. So when a die is rolled, our sample space, we have options of 1, 2, 3, 4, 5, or 6. Event A is going to be a number greater than 3. Event B is that we got an even number, and we want to know, are the events independent? So let's do it with the intersection way, with the and. So we want to know, is the probability of A and B equal to the probability of A times the probability of B? Now, we don't know if it's equal. We're trying to figure that out. So I'd like to put a question mark over the equal sign because we really don't know if they're equal yet. But let's find out. So probability of A and B, that would mean we want it to be both greater than 3 and even at the same time. So we need to look at our list and see how many are greater than 3 and also even. Well, that should just be the 4 and the 6. So that's 2 out of 6 total. Probability of A. They told us A was a number greater than 3. So we got to look at our list, see how many numbers are greater than 3. Well, there's 3 out of 6. Times probability of B on its own. Well, that's our even numbers. Well, that's 2, 4, and 6. So we also have 3 out of 6 for that. Well, now we just have to multiply and neaten these up. Even the one that has only one fraction, you always want to reduce it. Remember, your calculator will reduce things if you just type them in. So this is going to give us 1/3. Over here, if we type that in, we're going to get 1/4. So 1/3 is not equal to 1/4, so we would say that they are dependent. Okay, and you would also get full credit if you just said not independent. So either dependent or not independent would both give you full credit. Now let's show you the conditional ways. So probability of B given A, or you could do the reverse too. Probability of A given B should equal the probability of A. Okay, we'll just look at one of the ways to show you. So let's say we want probability of A given B. We want it to equal the probability of A. And we don't know. Well, the probability of A we had right here was 3/6. Probability of A given B with our scenario is saying, what is the probability of getting a number greater than 3 given that an even number is rolled? So because an even number is rolled, we want our list that we're going to look at to be only the even numbers. Well, now we want to look at that and say, okay, what is the probability of it being greater than 3? Well, of that list of 3 numbers, there's 2 of the 3. So then we want to see, are those two things equal? Well, this is 2/3. This is a half. Those are not equal. Therefore, that would also tell us this is dependent. So you can use either of those two options. We will tend to use the one on the left. So going down to the bottom, we'll pause for a minute and we'll let you read through that paragraph. All right, so the things that we're given, we've got 12% for hearing problems and listening through headphones. So maybe let's call hearing problems HP and we'll call headphones just H. So because it's an and, we know the probability of hearing problems and listening through headphones is 0.12. Other things we know, 60% listen to loud music on headphones. So we know that the probability of headphones is 0.6. Well, the thing we still need so we can do our independence formula is the probability of hearing problems. Well, they said 85% were found to not have hearing problems. So we have to think about if 85% do not have hearing problems, what percent would have hearing problems? And it's just the complement of that, what would add up to get us 100%, and that would be 15%, so we'd have 0.15. So now we want to see, is the probability of our and, hearing problems and loud music on headphones, is it equal to, again, I like to put the question mark on there because we don't know, the probability of headphones times probability of hearing problems. And all we'll do is we'll fill them in. We'll have 0.12 equals 0.6 times 0.15. Now when you have a decimal, you don't have to try and reduce that like you do with a fraction. And we'll give you a second on your calculators to type in the 0.16 times the 0.15 and see what it gives you. And we should have got 0.09 for that. They are not equal. So are the events independent? We would say no, they are dependent. So what that means again by being dependent, if we know one of those events is happening, it changes the probability of the other one. We don't necessarily know if it changes it to be higher or lower, we just know it changes it. So what that means is if you know someone has hearing problems, then that changes the probability of whether they listen to loud music on headphones. Or if we know someone listens to loud music on headphones, that changes our probability of whether they have hearing problems. So we don't know if it changes it more or less, but we know it just changes it. All right, moving on to page 60. We'll give you a moment to read through those. Sorry if the video went out there for a second. I kicked the cord. So we want to know if snow and rain are independent. So we're going to have to do the probability of snow and rain. And we want to know, is it equal to probability of snow times the probability of rain? So snow and rain would be the middle of the Venn diagram. So it's going to be 5 out of, and there's two ways we can figure out the total. We can add up all four numbers, which would give us 31, or in the question they helped us out and told us it was out of 31. Well, now what's the probability of snow? So you need to be careful when looking at Venn diagrams. We've got to look at the entire snow circle. And we've got to add up all the numbers in that snow circle. So we would have had 8 out of 31. And now for rain, we'll look at the entire rain circle. So inside that rain circle, we have 13 out of 31. And we'll type in each side. When we type in the left, it does not reduce. When we type in the right, we get 104 out of 961. Those are not equal, so we would say they are dependent. All right, moving down to the bottom, we've got a two-way table. First thing we should always look for in a two-way table is if we have the totals. And if not, we need to find those totals. But we do have the totals here, so we're good. What's the probability that a person chosen at random will be 31 to 45 years old? So we need to see how many 31 to 45-year-olds there are. And if we look in that row, there's 89. And if your numerator is one of the marginal totals, it can only possibly be over the overall total. So 89 over 207. Now the notation we would have for that, we would say like probability of 31 to 45. What is the probability that a person who makes over $50,000 will be 31 to 45 years old? So the notation for that would be probability that someone is 31 to 45. So we put the vertical line to mean given, and then makes over 50,000. So this means we want to look in the makes over 50,000 column only. And looking only in that column, what is the probability of being 31 to 45? Well, we've got 35 for the numerator and 96 for the denominator. Based on your answers above, is annual income independent of age? Well, if it was independent, knowing that someone makes over 50,000 should not affect the probability of 31 to 45. And if we look at our answers from A and B, it does affect it. It's changed. So we can say they are dependent since the 89 over 207 did not equal the 35 over 96. So that's the harder way, the conditional probability one. Now you could have done this with our and being equal to the individual ones. And let me just show you up here how you could do that. So our probability of being 31 to 45 and over 50,000, we would do 35 over our 207. And then we would say, okay, is it equal to our individual probability of being 31 to 45, which we had found is 89 over 207, times the individual probability of making over 50,000, which would have been the 96 over 207. And then we would have found that 35 over 207 is not equal to, and this ends up being 2,848 over 14,283. So you could have answered part C doing that way with the and showing whether it's equal or not to the individual ones multiplied, but we already had our answers for A and B to just make the argument with the conditional probability. All right, last one for the video today on page 61. We've got a spinner here, numbers 1 through 8. All of the spaces are of equal size. E is going to be the probability of getting an even. S is going to get a perfect square. Are the two events independent? All right, well, let's list our numbers. We got 1, 2, 3, 4, 5, 6, 7, and 8. So even. I'm going to underline the evens in green. Even, 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 even. Perfect squares, I'm going to underline in red. So perfect square is a number times itself equals that number. So example 25 is a perfect square because 5 times 5 gives us this. 1's a perfect square because 1 times 1 gives us 1. 4 is a perfect square because 2 times 2 gives us 4. The next one would be 9. It is not on our list. So we want to know, is the probability of being even and a perfect square at the same time, is it equal to the probability of even times the probability of a perfect square? So there's 8 total for each of these. So we know each of our denominators will be 8. So even and a perfect square. So we're looking for any ones that we underline twice. We'll notice that only happened with the 4. So it's 1 out of 8 is the chance for an even and a perfect square. Then probability of even. Those are the green ones. We underlined 4 of the 8. And then probability of a perfect square. Those are the red ones. We underlined 2 of those 8. So we want to know, are those equal? Well, this is 1/8. On the right, this will give us 8/64, which reduces to 1/8. They are equal. This was the test for independence. When they are equal, the events are independent. So that means if we know we split an even, it does not change the probability of whether it's a perfect square or not. And let's see why. In the whole sample space, it was a 2 out of 8, or in other words, 1/4 chance of a perfect square. If we looked at only the evens, there's one perfect square, so it's also 1 out of 4. Well, let's say if we reversed it. What if we looked at only the perfect squares? What's the chance of getting an even? Well, in the original, the even is 4 out of 8, or 1/2. If we look at only the perfect squares, one of them is even, so it's also 1/2. So knowing one of them did not affect the probability of the second thing. All right, that's it for this video. You got your 2 homework problems. Have a great rest of your day.